My sincere greeting to one and all. I am Tamanna from BSc Chemistry Honors second year. Today I am here with chapter Chemistry of Elements of second and third transition series. In the previous chapter we have discussed the position of transition elements in the periodic table. Transition elements belong to D block of the periodic table and are located in between the S block and P block elements in the periodic table as shown in figure 2.1. The D block elements involve primarily the filling of D subshells. The penultimate cell in these element is also being expanded from 8 to 10 electrons by the addition of 10 electrons. We also attempt to define the transition elements as elements which have partially filled D or subshell, either in their elementary form or in their common occurring oxidation state. Strictly speaking, the definition excludes zinc, cadmium, and mercury from the D block elements. This is because these elements do not have partially filled D subshell, either in their elemental form or in their common oxidation state. The elements of group 12 do not show distinctly the properties of transition elements except for their ability to form coordination complex with ligands. However, for the sake of continuity and rational classification of the element of group 12 are included in D block elements. In this chapter, we intend to explore the chemistry of heavier metal of D block. Example, second and third transition series. The higher metal of the D block are highlighted in figure 2.1. It is interesting to note that, like the 3D transition series, the atomic number of the elements of second transition series Y to CD are filled sequentially from 29 to 48. However, there is discontinuity in atomic numbers between electronoid Z is equal to 57 and HF Z is equal to 72 in the third transition series. In brief, the second and third transition series that involve the filling of 4d and 5d orbital respectively include the element with atomic number. Second transition series deuterium Z is equal to 39 and cadmium atomic number is equal to 48. Fourth orbital 4d orbitals are gradually filled. Third transition series lithium atomic number 57 to hafnium and atomic number 72 to mercury atomic number 80 are 5d orbitals are gradually filled. Electronic configuration of elements of second and third transition series. The general electronic configuration of element of second 4d and third 5d transition series can be written as n-1d 1 to 10 n s 1 to 2, where n-1 stand for the penultimate shell which occupy 1 to 10 electrons of the d subshell, while n stand for the outermost shell that occupy 1 to 2 electrons in the s orbital. Table 2.1 listed the ground state of electronic configuration of elements of the second and third transition series. Deuterium. It is important to mention that the elements of group 7, 8, and 9 are collectively called the platinum group metals. General characteristics of second and third transition series. We have noticed clearly predictable trends down each group in the chemistry of S and P block elements. However, transition elements of second and third transition series, the element of period 5 and 6 show very strong similarities in their chemistry within a group but show large differences from the element of the transition series. This similarity is due to the filling of 4f orbitals in elements that lie between these two elements period 5 and 6. Electron in these orbitals shield very poorly and the electron in the outermost 6s and orbital. As a result of poor shielding, the effect of nuclear charge decreases with the result that the covalent and ionic radii of period 6 element are reduced at almost the same of those of s period. Let us discuss the important difference in and their causes. First, irregular and anomalous electronic configuration. In the first transition series, the 4s electrons are filled before 3d electrons in the neutral gaseous atom from secondum atomic number 21 onward to 3D level continues the to filling regularly with increasing Z, but chromium there appears to be a anomaly. In case of chromium, the electrons are filled that the 4s and d orbital are each half filled. This is due to the extra stability associated with half filled orbitals. Similarly, copper, the electronic configuration is anomalous because of extra stability associated with completely filled d orbital. However, elements of the second and third transition series display much more irregular electronic configuration in addition to half or completely filled d orbital. These are shown in bold letters in table 2.2. The irregular trend of electronic configuration occurs in chromium, copper, rubidium, platinum. The anomalous electronic configuration of elements are attributed to the several electron repulsion, atomic and ionic radii. The atomic and ionic radii of elements of first transition series 3D are well known. However, the atomic and ionic radii of second and third transition series element are not known with certainty with the exception of few elements. As we move down a particular family of the transition metals in the period group, there is an increase in size from first to second transition series, but the size increase from the second to the third transition series is negligible and shown in table 2.3. Oxidation state. The oxidation number of transition metals are higher for the first half of each row than the later member. Lower oxidation state are found to be more stable. Element of second and third transition series. The element of second and third transition series have higher or common oxidation number than the first transition series as shown below. Like the main group element, the highest oxidation number of transition metals is found in case of oxides. Thus, the highest oxidation state is +8 occurs in case of osmium, OS4 negative. For the other compounds that exist in higher oxidation state, which have no counterparts in the first row of WCl6, ReF6 or PtF6. It is also interesting to know that superficial similarities in the chemistry of second and third transition series element exist compared with the element of first transition series. For example, chromium, MO, and W all form the oxidation oxides with oxidation number +6. However, for chromium 6 oxide with CrO3 is highly oxidizing, where MoO3 and WO3 is normal oxide of this metal. Reactivity. The elements of first transition series are more reactive than the corresponding element of second and third transition series. The lanthanide contraction is majorly responsible for the low reactivity of second and third transition series. As an example, gold and platinum are very less reactive. The low reactivity is due to the closeness of the vacant electrons to the nucleus because of poor shielding effect of 4f electrons. Because of the poor screening of 4f electron, the valence electrons are tightly bounded to the nucleus and are not readily available for chemical reactions. Fifth, stability of the complex. Transition metals have the ability to form complex in contrast to S and P block elements. This is due to the small size, highly charged ion, and availability of vacant d orbitals of low energy in the case of transition metals. The elements of first transition series form stable complexes with hard donors wise NO and F, where the element of second and third transition series form more stable complex with phosphorus, sulfur, and heavier uh, chalcogen donors. Coordination number. The coordination number 6 is commonly found in transition elements giving an octahedral structure. The coordination number 4 is less common compared to coordination number 6 to give either square, planar, or tetrahedral structure. Complexes with coordination number higher than 6 are less common for the first transition series but are common among early member of the second and third transition series, ligand repulsion interaction become more important with higher coordination number, and thus it is the smaller ligand which allow highest coordination number. There are only few compounds in which the coordination number is 7. There are three geometric form known in this case and are shown as monocapped octahedron, pentagonal bipyramid, and tetragonally capped trigonal prism, as shown in figure 2.2. The capped octahedron is shown by tungsten 2 complex wise WBr3CO4 all over negative, or by NBOF6 3 negative. The capped octahedron is formed by the addition of a seventh atom to the center at the center of the any face of the octahedron. The pentagonal bipyramidal geometry is adopted by the ionic species, and tetragonal cleft trigonal prism is adopted by MF7 to negative, where M is equal to NB or Tm. This arrangement is made by putting a seventh atom above the central and one of the rectangular face of the trigonal prism. Coordination number generally Coordination number greater than 7 or also known among the second and third row transition elements. Uh, Coordination number 8 is found in the square antiprism as in Na3 MOCN8, and in this dodecahedron as in Bu4N3 MOCN8, as shown in figure 2.3a. It is important to note that the solid state structure is sometimes influenced by the counter ion, as in case of Na3 MOCN8 and Bu4N3 MOCN8. Coordination number 9 is the limit for covalently bound block metal complexes, because this represents the full use of the 9 valence orbitals 1s and 3p and 5d orbitals. The anion REH 9 2 negative has a tricapped trigonal prismatic structure with coordination number 9 as shown in figure 2.3b. Seventh, aqueous chemistry. Elements of the first transition series have a very rich aqueous chemistry. As an example, cobalt 2 form a variety of tetrahedral and octahedral complexes and display interesting and aqueous chemistry. On the other hand, corresponding members of the second and third transition series from RS2 to IR2 do not form such complexes and consequently do not have the aqueous chemistry. However, most of the heavier transition metals, instead of forming simple cationic complex, prefer to form ionic complex in the form of oxo or halo complexes. The ionic complexes of heavier transition elements have rich aqueous chemistry. Its magnetic properties: compound with no unpaired electrons are diamagnetic, while those with one or more unpaired electrons are paramagnetic. Most of the transition metal compound are paramagnetic. The diamagnetic behavior arises from the cir- uh, circulation of electron pair introduced by the presence of applied magnetic field. This charge circulation produces an induced magnetic moment, and which opposes the applied field and leads to the atom ion or molecule being repelled by it. On the other hand, the unpaired electrons are present. The applied field induces a magnetic moment which is aligned with the magnetic field. This effect causes the simple to be attracted into the magnetic field. Paramagnetism results from the interaction of the spin and the orbital angular momentum of the electron, which is the applied magnetic field. There is no interaction coupling between the spin and orbital angular momentum. The magnetic momentum mu s plus L of one atom or ion is related to the total spin quantum number s and the total angular momentum quantum number L by the expression mu s plus L is equal to under the root g square into s into S plus 1 plus L into L plus 1. The magnetic behavior of element of second and third transition metal ion is more complicated to explain, as one has to take into consideration both the spin orbital coupling and the effect of covalent character in metal ligand bonding, where G represents the geometric ratio magnetic ratio for free electrons. Its value is 2.00023 or partially 2. Therefore, the above equation reduces to mu s plus L is equal to under the root 4s into s plus 1 plus L into L plus 1. The unit of magnetic moment mu s plus L is Bohr magneton Bm. In case where the orbital angular momentum contribution is quenched so that 4s into s plus 1 is greater than L into L plus 1, this expression 2.2 becomes mu s is equal to under the root 4s into s plus 1. This is the fact that spin only value of magnetic moment. This provide a good approximation to the observed magnetic moment mu for the first row transition metal complexes, and is generally found to be mu g is less than or equal to mu osh, less than or equal to mu s plus L, as shown in table 2.5. In the case of high spin d ion such as Mn2 positive or Fe3 positive, L is equal to 0, so that these electrons in the complex can be easily calculated and the magnetic moment value can be evaluated. Question: calculate the magnetic moment mu s plus L for Cr2 Cl3 positive plus O3 positive ion in the absence of crystal field. And B is calculate the spin only magnetic moment of Ni2 positive in NiH2 or 6 2 positive. The magnetic answer A part का the magnetic moment of the metal ion can be calculated from its S and L value according to equation mu S plus L is equal to under root 4s into S plus 1 plus L into S plus L plus 1. From the diagram given below, the value of mu S plus L for different values of S and L can be calculated. Ninth, metal bonding. Metal bonding is very rare in first transition series except in metal carbonyls such as MnCO, Fe2CO9, Fe3CO12 and CO4CO12, and in carboxylate complexes such as chromium 2 acetate and solid nickel dimethyl diglycosamine. On the other hand, metal bonding is very common among the heavier transition elements in second and third transition series. For example, first, they form carbonyl with metal bonds similar to those of first transition series wise. In addition, it forms rubidium 6 CO12 16. The heavier metals such as MO, Ru, and RH form binuclear carboxylate complexes such as MO2CH, COO4, H2O twice. The halides ion are of type R2Cl8 negative and MO2Cl9 3 negative possesses metal bond. A unique feature of the set of 5 elements of second and third transition series is that these form clusters in which there is extensive metal bonding. The complex cations and have such the complex cation Nb6Cl12 2 positive and TH6Cl12 2 positive have unusual structures. Both the cationic species can contain 6 metal atoms arranged in a cluster to at the corners of an octahedron, which with 12 bridging halogen atoms across the corners. In these clusters there is an extensive metal bonding as shown in figure 2.4. Unlike the lower halides of 3D series, the lower halide of MO and W exist as hexamers, and these present interesting structures where M is equal to MO and W is equal to X Cl Six metal atoms are arranged in a cluster at the corners of a octahedron with eight halogen atoms located above each of the eight faces of the octahedron and bonded to three metal atoms as shown in figure 2.5. Chemistry of ReCl3 is interesting as it exists as a trimer R3Cl9. It consists of a triangle with three Re atoms with three bridging halogen atoms across the three corners and six halogen atoms that bridge to other R3Cl9 unit as shown in figure 2.6. Tenth abundance. All the 10 first row transition elements are widely distributed throughout the earth crust and the oceans. Iron is the fourth after oxygen, silicon, and aluminium. Titanium is the ninth, while magnesium is the 12th most abundant element by weight in the earth crust. The remaining transition element of second and third transition series are very scarce and taken together. These 20 elements constitute only 0.025% of Earth crust in comparison with 2.6 of all the 10 first row transition elements. Molybdenum is a unique element among the second and third transition series that play an important role in human body. Technetium Tc does not occur in nature. Ionization energy. The first ionization energy of an atom is the minimum energy required to convert 1 mole of the gaseous atom in its ground electronic state lowest energy into 1 mole of gaseous unpositive ion. The amount of energy required in the process indicate how strongly the atom most loosely bounded electron is attracted by the nuclear charge. It has been observed that in case of with which an electron can be removed from a transition metal atom is intermediate between those of S and P block elements. The first ionization energy and the successive second and third ionization energy of the transition elements are plotted in figure 2.7. An inspection of the figure 2.7 carefully reveals that the third ionization energy increase more rapidly than the first and second ionization energy. As a result, these transition metals are better indicated by third ionization energy. The variation of third ionization energy of these three set of transition elements from scandium to zinc, Y to cadmium and La to Hg shows that there is a general increase in the ionization energy with a discontinuity after group 7. This discontinuity in the value correspond to the uh, ionization from a doubly occurred occupied d orbital. Example, the electronic configuration of iron atomic number 26 is 3d64s2. Example, the third ionization from the atom of group 8 to 12 are formed doubly occupied d orbitals and are consequently lower because of the increasing repulsion between the paired electrons in the same orbitals in the subsequent elements. This discontinuity between manganese and iron in the first transition series and between technetium and deuterium in second transition series reflect addition energy required to break into the half-filled D5 subshell in Mn2 and Tc2 positive, which involves the maximum loss of exchange energy. Similarly, in the case of europium, the third ionization potential does increase in the third transition series where the 4f configuration is reached. Therefore, thereafter it falls back and then increase again on approaching 4f14 configuration at WYB2 positive. In brief, the ionization energy increases irregularly across the three transition series and is for less regular in third transition series. Question second. Why is the ZrCl4 is most stable chloride of zirconium where the palladium is it PdCl2? An inspection of the third and higher ionization energy of the d block element reveals that the Ionization energy of the element increase in with increase in atomic number of the element due to the large effective nuclear charge ZeF. This causes the third and higher IP of palladium very high, which makes it energetically unfavorable. In addition, toward the end of the transition series, the d orbital become more core-like. As a result, these are less effective in stabilizing higher oxidation state through covalent contribution of bonding taken together. These factors make higher oxidation state less accessible to the right of the d block. In addition, there is greater loss of exchange energy in creating palladium 4 positive from palladium 2 positive than Zr 4 positive from Zr 2 positive. Comparative study of the element of second and third transition series. We have already discussed the journal characteristics of the elements of second and third transition series with special reference to the elements of the first transition series in the preceding section. In this section, we will like to highlight the chemistry of elements in different groups of second and third transition series. An attempt will also be made to compare the chemistry of these elements with the elements of first transition series. Group 4, Zirconium Zr and Hafnium HF. Group 4 consists of elements titanium, zirconium, and hafnium. Some of the unique properties of these elements are summarized below. Electronic configuration of the three elements: atomic radii, ionic radii, melting point in Celsius, boiling point in degree Celsius, density in gram centimeter inverse cube, electronic gravity, electronegativity. We have already remarked that the atomic and ionic radii of the transition elements in a particular series decreases with the increase in atomic number. However, compared to the S and P block elements, the decrease in the radii along a particular series is not regular and uniform. In case of group 4 element, both zirconium and hafnium have larger atomic and ionic radii than titanium. However, an inspection of the table reveals that the both of the atomic and ionic radii of zirconium and hafnium are identical. As a result, these elements have similar chemistry. This is primarily attributed to the effect known as lengthened contraction. All these elements possess outside a noble gas core D2S2 configuration. The significant difference between zirconium and hafnium from titanium is that unlike titanium, zirconium and hafnium only form a few compounds in oxidation state below 4. Most of the stable compounds are in oxidation state 4. Both zirconium and hafnium form the binary tetrahalides. The tetrahalides can be prepared by the standard method. All the tetrahalides in the gaseous state are monomeric and tetrahedral, but in solid state these are octahedral coordination through halogen bridging. The tetrahalides are readily hydrolyzed. The extent of hydrolysis, however, decreases from titanium to zirconium. TiX4 compound are hydrolyzed to TiO2, whereas zirconium ZrX4 and HFX4 hydrolyzes to give ZrOX2 and HFOX2. Zirconium chloride 4 is hydrolyzed vigorously by water at room temperature to give oxachloride, which is stable to further hydrolysis. The complex ZrOCl2 into 8H2O, which crystallizes from dilute HCl, have been shown in X-ray that contain the ion as shown below in figure 2.8. Each zirconium atom is surrounded by 8 oxygen atoms, 4 oxygen from 4 coordinated water and 4 oxygen from breathing OH group. The coordination number of each zirconium ion in the complex is 8. Like titanium 4 chloride, ZrCl4 and HFCl4 are known to act as good Lewis acid, therefore they react with neutral reagents to form the stable aggregate of the composition MX4 into 2L, where L is triphenyl phosphine ether, etc. Zirconium and hafnium have a high charge in +4 oxidation state. There is no partially filled d subshell that might give stereochemical preferences and have relatively large size 0.74 and 0.75 angstrom. As a result, the tendency to assume higher coordination number increases with zirconium and hafnium. Example with the coordination number reaches 7 or 8 are known with oxygen and fluorine ligands. For example, the table is given below. The structures of anions ZrF73 negative and ZrF84 negative are shown below in figure 2.9 and 2.10. 10. The species ZrF73 negative is basically a trigonal prism with an extra ligand attached to one face. There are a variety of other 8 coordination complexes. In case of zirconium, the 8 coordinate complexes of the following: carboxylate, acetal acetonates, oxalates, nitrates. Oxidation 3. State 3. The reduction of the tetrahalides by the respective metal at high temperature and pressure yields the tetrahalides, which are colored complexes. The well-known compound of three oxidation states are ZrCl3, ZrBr2, Br3, ZrI3, HFCl3, and HFBr3. Group 5: Nobinium, Nb, and Tellurium, Ta. Group 5 consists of the elements vanadium, nobinium, and tantalum. So, some of the unique properties of these elements are summarized below. Element, their electronic configuration, atomic and ionic radii, melting and boiling point, density, and electronegativity. Nobinium and tellurium occurs generally together and are separated by fractional crystallization of their fluorocomplexes. The atomic and ionic radii of nobinium and tellurium are almost similar but greater than that of 3D analogous example vanadium. Although both nobinium and tellurium are metallic in their chemistries, in the vanadium oxidation in 5 oxidation state are more similar to those of typical non-metals. As a result, they do not form cationic complexes characteristics of a metal. Instead, they form a variety of anionic complexes typically a non-metal. The coordination number of nobinium and tellurium in their ionic complex are generally 7 and 8. The stable binary oxide of nobinium and tellurium are the pentaoxides M2O5, where M is equal to Nv and Ta, which are dense without powders. These are obtained by the ignition of other nobinium and tellurium compounds in air. They are very stable oxide and extremely difficult to reduce. Halides and oxohalides. Nobinium and tellurium forms all the halides in their high oxidation state. The pentafluorides are obtained by the reaction. A unique feature of nobinium is that it is formed the stable pentaiodide. The pentafluorides are volatile white solids melting below 100 degrees Celsius and boiling near 230 degrees Celsius. They have a tetrameric structures that is characteristic for other pentafluoride with MF6 unit and one bridging fluoride between each pair of metal atom as shown in figure 2.11. The pentachlorides are yellow crystalline solids that are obtained by the direct reaction of the metal with chlorine. X-ray study reveals that NbCl5 is a dimer in the solid state with two bridging chlorides giving an octahedral configuration around each nobinium. The halides are readily hydrolyzed to give oxyhalides of the formula MOX3, where M is equal to NbOTA. The oxo halides are covalent but less volatile than the corresponding pentavalent halides. The structure of NbOCl3 is polymeric and shown in figure 2.13. The oxychloride contains planar trinuclear groups which are linked into long chain by oxygen bridging between the niobium atom. Niobium pentachloride Nb2Cl10 is reduced by pyridine to give nobelium 4 complexes of the type NbCl4 pyridine 2. Both the pentafluorides are strong Lewis acid and give adducts with neutral donors. They also form complex anion with halide ions. For example, both the pentafluoride form fluorocomplexes lower halides. The lower halides of nobinium and tetralium deserve special mention. The lower halides are prepared by the reduction of the pentahalides either by heating with the metal itself or with aluminium. Earlier, it was considered that the lower halide of Nb and Ta were non stereochemistry. However, it has been shown that most of the lower halides are in fact cluster compounds containing the basic unit M6X12 2 positive. The octahedral M6 unit are held together by MM metal bonds over the six metal atoms in addition to halogen bridging along the 12 edges of the octahedron. An interesting example of the lower halide of nobinium is Nb6Cl14. It is made by reducing nobinium pentachloride with cadmium metal at a red heat, dissolving the product in dilute HCl and recrystallizing from the solution. The cadmium is precipitated as cadmium sulfide. The chloride Nb6Cl14 consists a discrete ion Nb6Cl12 2 positive as shown in figure 2.14. Group 6, molybdenum and tungsten. Group 6 consists of element chromium, molybdenum and tungsten. Some of the silent features of these elements are summed up below. Molybdenum and tungsten have the atomic and ionic radii nearly similar but possessive greater value than corresponding first element chromium in group 6 on account with similar radii value of MO and W possesses nearly similar chemical properties. Group 6 element display valencies ranging from group 6 plus 6 down to 0. The valency plus 6 is the highest of all the elements. Molybdenum and tungsten in the plus 6 state are the most stable and the most common state. It is important to note that in case of chromium, the plus 3 state is the most common and the most stable state. It follows that the higher valent chromium, especially in the plus 6 state, will be strong oxidant. In fact, chromium in the plus 6 state is the strongest oxidation agent. On the other hand, MO3 and W3 are strongly reducing. The trioxide of MO and W are obtained by heating with the metal or the compound in air. MoO3 is white whereas WO3 is yellow solid. Unlike CrO3, the trioxide of MO and W are insoluble in water. MoO3 and WO3 are not attacked by acid other than HF. In alkaline medium, they dissolve to form molybdates MoO4 negative and tungstenates WO4 negative. They are tetrahedral in shape. Condensation of oxonium ion molybdate and tungstate give polyoxamine and polyoxometalate in the presence of acid. Some of the well characterized molybdates and tungstenate ions are the structures of polymolybdates and polytungstenate are based on MoO6 and WO6 octahedra by sharing of oxygen atom. Anions such as MoO42 negative or WO42 negative containing only one kind of metal atom are called isopolyanions, whereas ions containing more than one element metal atom are called heteropolyanion. An interesting example of heteropolyanion is found during molybdenate test of phosphate when allo precipitate are formed of the composition. Thus, the heteropolonium of is PMO12O43 negative halides. The interaction of molybdenum and W with elementary fluorine gives colored covalent hexafluorides MO6 boiling point 35 degrees Celsius with WF6 boiling point 17 degrees Celsius chlorinates in molybdenum gives only the dark reddish dimer pentachloride solid MO2Cl10. It has a structure similar to that NB2Cl10 as discussed earlier. The molybdenum and tungsten dichloride dibromide and diiodide are hexameric are the solid state of halide bridged cluster. The cluster of isostructural with iron are discussed earlier. The structure also contain metal bonding in MO6 cluster. In lower oxidation state there is a great tendency of metal bonding in case of molybdenum and tungsten 3 forming MO2Cl9 3 negative and W2Cl9 3 negative ionic species wherein in MCl6 octahedrons share a face as shown below. In the corresponding Cr2 or Cl9 3 negative ion, the CrCr distance is 312 pm. It shows that the normal magnetic moment corresponds to 3 unpaired electrons. In further implies that there is no CrCr bond in Cr2 Cl9 Cl negative. On the other hand, the low magnetic moment value is MO2 Cl9 3 negative is particularly diamagnetic character in case of W2 Cl9 3 negative suggests appreciable metal bonding in case of molybdenum and tungsten ions. This is further supported by bond distance in case of molybdenum to 67 picometer and tungsten to 42 picometer compared to 312 picometer in case of chromium. Interaction of molybdenum hexachloride MoCO6 with carboxylic acid give a dimer MO2OOCr4 with a unique tetra bridged bonding treatment with MO2OCOR4 with KCl and HCl yields to a compound containing a unique anion MoCl8 4 negative. The bonding between the two molybdenum atoms shows above is called quadrupole bonding. Involve it involves 1 pi and 1 sigma and 2 pi bonds and 1 sigma 1 del bond between two molybdenum atoms. It is interesting to note that the two MOX4 units show in the figure 2.17 are ellipsed configuration of each other. Overall summary of the chapter. First, transition elements are D block elements. The D block elements in the fifth period are referred to the second transition series. The D block element in the sixth period constitute third transition series. For difference between electronic configuration written from periodic table and observed calculated electronic configuration occur only when energy levels are closely spaced. The ground state electronic configuration of ions can be written in the form of ground state electron configuration of the atom. Transition metals are shiny, malleable, and ductile and conduct thermal energy and electricity. The separation of metal from their ores, making of alloy, are all part of metallurgy. Most of the transition metal have more than one oxidation state in their compound. The defined oxidation state differ often by 1 unit. Majority Majority of the transition metal compound are colored and paramagnetic. Measurement of paramagnetism can be calculated to find the number of unpaired electrons in the species. Transition metal have a strong tendency to form coordination complexes. The coordination number of the metal ion in a complex represent the number of atoms or groups are firmly bound to the metal ion, the number of ligands. The valence bond theory accounts with the geometry of complex. It can be used by be made explain the number of unpaired electrons. It is the promotion of electrons from lower energy d orbital to higher energy d orbital that results the color of the transition metal complexes. The difference in energy between d orbital is large in case of strong field complexes. Atoms of element of the second and third transition series are about the same in size because lengthenoid contraction. The lengthenoid contraction is the slow and steady decrease in the atomic and ionic radii with the increase in the atomic number of the lengthenoid series. Second and third transition series elements that are in same group are usually more like other than they are the element in first transition series. Label complexes readily exchange ligands with the solvent. The complex does not exchange ligand readily is called an inert complex. Metal-metal bonding is very common among the heavier transition elements of second and third transition series. A set of five elements Ynobidium, Ta, Mo, W, and Re and second and third transition display a unique feature of forming clusters in which there is an extensive metal bonding. Thank you.